how can it be prevented? If you've watched a lot of disaster films, you might have the idea that building collapse is caused directly by the ground beneath them shaking violently or even splitting apart. But that's not really how it works. For one thing, most buildings are not located right on a fault line, and the shifting tectonic plates go much deeper than building foundations. So what's actually going on? In fact, the reality of earthquakes and their effect on buildings is a bit more complicated. To make sense of it, architects and engineers used models, like a two-dimensional array of lines representing columns and beams, or a single-line lollipop with circles representing the building's mass. Even when simplified to this degree, these models can be quite useful, as predicting a building's response to an earthquake is primarily a matter of physics. Most collapses that occur during earthquakes aren't actually caused by the earthquake itself. Instead, when the ground moves beneath a building, it displaces the foundation and lower levels, sending shock waves through the rest of the structure and causing it to vibrate back and forth. The strength of this oscillation depends on two main factors: the building's mass, which is concentrated at the bottom, and its stiffness, which is the force required to cause a...
So my basic concern will be related to the building's strength and the stiffness of the building. Now, as you have seen all these sessions, this is your 14th session. So when you say a structure has to resist an external input, mute kar do, jiska awaaz आना है. So that structure has to resist its external force of earthquake in the terms of the inertia force, the damping force, and the stiffness forces there. So if we have seen in the previous historical monuments, they are having a huge mass, like the thickness of how Sir was saying that Taj Mahal. The Taj Mahal, the thickness of the walls is very larger. It might be larger than 1 meter. Like your China wall is there. So that is also having a large thickness. So why these structures were made larger? To increase the strength, and strength of that structure can be increased by increasing the mass of the structure. So the external force of earthquake is being resisted by the mass and the stiffness.
Certain amount of displacement. Along with the building's material type and the shape of its columns, stiffness is largely a matter of height. Shorter buildings tend to be stiffer and shift less, while taller buildings are more flexible. You might think that the solution is to build shorter buildings so that they shift as little as possible. But the 1985 Mexico City earthquake is a good example of why that's not the case. During the quake, many buildings between 6 and 15 stories tall collapsed. What's strange is that while shorter buildings nearby did keep standing, buildings taller than 15 stories were also less damaged, and the mid-sized buildings that collapsed were observed shaking far more violently than the earthquake itself. How is that possible? The answer has to do with something known as natural frequency. In an oscillating system, the frequency is how many back and forth movement cycles occur within a second. This is the inverse of the period, which is how many seconds it takes to complete one cycle. And a building's natural frequency, determined by its mass and stiffness, is the frequency that its vibrations will tend to cluster around. Increasing a building's mass slows down the rate at which it naturally vibrates, while increasing stiffness makes it vibrate faster. So in the equation representing their relationship, stiffness and natural frequency are proportional to one another, while mass and natural frequency are inversely proportional. What happened in Mexico City was an effect called resonance, where the frequency of the earthquake's seismic waves happened to match the natural frequency of the mid-sized buildings. Like a well-timed push on a swing set, each additional seismic wave amplified the building's vibration in its current direction, causing it to swing even further back, and so on, eventually reaching a far greater extent than the initial displacement. Today, engineers work with geologists and seismologists to predict the frequency of earthquake motions at building sites in order to prevent resonance-induced collapses, taking into account factors such as soil type and fault type, as well as data from previous quakes. Low frequencies of motion will cause more damage to taller and more flexible buildings, while high frequencies of motion pose more threat to structures that are shorter and stiffer. Engineers have also devised ways to absorb shocks and limit deformation using innovative systems. Base isolation uses flexible layers to isolate the foundation's displacement from the rest of the building, while tuned mass damper systems cancel out resonance by oscillating out of phase with the natural frequency to reduce vibrations. In the end, it's not the sturdiest buildings that will remain standing, but the smartest ones.
So this video is available on the YouTube also to explain you the concept that why the buildings fail in earthquake. So I have shown you that video where the lack of strength and the ductility due to poor detailing of the reinforcement. Basically, I am speaking related to RCC buildings is there, and the introduction how you do is the design efficiency. Design efficiency is caused due to the failure to understand the failure mechanism, deficient system of calculation. So what we study in our analysis, structural analysis, this is what is that. If your analysis is done incorrect, then the bending moment, the shear force coming on the beams or columns are calculated incorrect. Based on that, if you design a structure, then that design will also be a incorrect one. So that causes a design deficiency, which precautions has to be taken by the structural engineer while doing the calculations or for the design of the structures. There is one more is that even if your design is correct, there might be some construction deficiencies like in the form of the lack of the quality assessment or quality control in the material or in the construction details, etc. So these two causes are also to be considered if, in the case when the buildings fails in the earthquake is there. So what are the challenges in the seismic design is that the seismic design is a challenging, or the earthquake resistant design of any structure is very challenging because our input is random. We are not knowing how the input is there. It is uncertainty is there. We don't know how much magnitude earthquake will come, for how much period it will long. We are not know. Based on the past records, whatever the earthquake zones are being created in the IS codes or in the other codes of the world is there. But we don't know in future how it is going to be happen. So the structural response depends on the input motion, that is how the earthquake motion is going to there, and also it depends on the structural properties, like we say in the terms of the stiffness. The stiffness is basically a property where the height of the building and the cross sectional dimensions of the building and the material of the building has to be considered. There is uncertainty in the input also, what I was telling you, where the next earthquake will occur, on what fault it will occur, on of what magnitude it will be there, nature of the ground shaking near the source, that is where the epicenter is there, how the nature will be there, effect of travel path on shaking at a distance. And also most important part what we have seen in the video is that when you are making an earthquake resistant structure, it is not only a responsibility of a structural engineer, but it has to go in a group hand to hand with the architect as well as with the geological engineer also. So the effect of local geology and the topography and the soil profile has to be considered, which was discussed by Dr. Nilima Satyam in her previous talk also. And there is also uncertainty in the structural properties, like we say uncertainty in input motion also. There is uncertainty in the structural properties also, like natural period or the stiffness of the structure, damping, soil structure interaction, and the post yield behavior. So how your structure is there, these all things has to be studied. And if these uncertainty of the structural properties are studied correctly, then definitely your structure will not get collapse. It will bend, but it will not get collapse. So therefore, several assumptions and simplifications are made in the seismic design processes. So the objective of earthquake resistant design, as we know that severe earthquakes are rather infrequent is there. So whenever a lifetime of a structure is there, it may happen, it may not come to the severe earthquake. It will not face any severe earthquake. So the probability is very low to the strong shaking during its lifetime of the structure. The next part is that should the structure be designed to withstand strong shaking without sustaining any damage? Yeah, if the probability is very less, and if you are designing a structure to such a strong shaking, what is going to happen? You are constructing your structure too expensive for that ground shaking, strong ground shaking is there. Then what is the next option is that it may be logical to accept some damage in the case of strong but infrequent shaking. So the our aim in the earthquake resistant design is that the loss of life and the content in the structure must be protected even in the case of the strong shaking is there. So the final aim what we have seen in all these sessions of the FDP, that our aim in the earthquake resistant design is that your building shouldn't get collapsed, that is there must not be the loss of life and the property is that your structure should stand, or there might be some structural damages but which were can be done a repairable one. Okay. So these are some historical examples which are earthquake resistant from last number of decades. They are standing and they have resisted the number of earthquakes like Taj Mahal, the Egypt pyramids are there, the China wall, Qutub Minar, and so on. All we know that these all structures, if we see in the terms of the earthquake resistant design, these structures are basically the having a mass. If we have seen in the video that if you increase the mass of a structure, so all these examples are to increase the mass of the structure. But nowadays it is not possible that you making 1 meter wide of the wall is there, because as the land is decreasing, how you can make a wall of 1 meter thick is there. So you have to go for some lightweight materials which are now basic in the advancement stages there, which are mostly used in the earthquake resistant design of the structures is there. So what is an earthquake engineering is that the application of civil engineering to reduce the life and the economic losses due to earthquakes. So the aim is this only. When you say an earthquake engineering, it is a part of an civil engineering, okay, and the aim is to mitigate the seismic risk is there. So what is the seismic risk from the engineer's perspective? The probability of losses occurring due to the earthquakes within the lifetime of a structure. These losses can include human lives, social and economic disruptions, as well as material damages there. So the seismic risk, you have to reduce the seismic risk. So seismic risk is in what terms? It is in the terms of the human lives, social and economic disruptions, as well as material damages there. So whenever a collapse of a structure is there, so there is a loss of material also you have to consider. So this risk is nothing but it is a seismic hazard and the vulnerability of that structure. So if I say seismic hazard, it is a probability of potentially damaging earthquake effect occurring at the site of a planned construction within its design life. So the design life is very important, and that is in the terms of the probability. कब आएगा कैसे आने वाला है, so it is in the based on the probability, the uncertainty is there, and based on this seismic hazard, the vulnerability of that risk is then is the probability of occurrence of the damage in the building when exposed to a particular earthquake effect is there. So this is what the seismic hazard is caused by nature, which cannot be reduced. Okay, but the vulnerability can be reduced, and that is what the man or the earthquake engineering or the structural engineer is doing. That can be reduced through proper seismic design of the structure is that. So this thing I will just show you the slides. It was already discussed by number of the experts in our FDP program. There they have shown the effect of earthquake which causes damage like ground shaking, surface rupture is there, the landslides are there, the liquefaction effect is there, the tsunami is there, and finally it may happen that there is a fire also. So I am skipping this fastly. This slide shows the damage versus collapses there. So the earthquake induced forces can be far larger than what we design our structures. So hence the damage is unavoidable during an earthquake. So we can't avoid it, but designing of an earthquake resistant does not mean you are making an earthquake proof structure is that, but by you can avoid the collapse by proper designing and detailing is there. So how you can do it in the global sense of collapse prevention is the one thing what in the very first slide I have discussed with you is the lack of the deficiency in the design is that it can be prevented by providing a proper redundancy in the structure and also by proper detailing in the form of the ductile detailing is there. So this part also it was discussed by this slide you might have seen by various experts have shown you that structure should able to resist minor. So minor shaking is that with no damages there. Moderate shaking, if you see that there are some damages, but they are non-structural damages. You can see here in the machinery damages is there, but there is no structural damage in the case of the moderate structure. And in the case of severe shaking is that there are structural damages, but final aim what we want is that it should not get collapse. So the final aim how we can do is that without collapse, the aim what in the buildings or in any structure is this part, that is this considers the account of high strength and high stiffness. So my aim of this presentation is to tell you about the effect of strength and the stiffness requirement of the structure is there. So when a structure experiences severe damage, it's not no longer remain elastic, but it has to rely on the property of undergoing large plastic deformation, which was discussed by most of our experts, and they have shown you the force deformation diagrams also, where in the case of an plastic deformation is there in the structures is there. So in this case, without significant loss of the strength is there, and that part what you do is the ductility is there. So structure should be ductile enough to resist the severe shaking without the collapse is there. So ultimate aim of an earthquake resistant structure is to make it one is the proper designing and the second one is the ductile detailing. So I will just discuss some basic part in very short span, that the ground acceleration occurs at the base of the structure. All of we know that there is it occurs at the base of the structure, and then due to that the structural vibration is due to the inertia forces, that is the mass of the structure is there, that is your mass into acceleration is there, and the force generated at the floor mass level is there. This part is important, that as your earthquake is in the lateral direction, in the horizontal direction, so the lateral members are the slab, or you can say in other words like your diaphragm is there. So in that case, they are the force first of all transferred to this floor masses level. So suppose your building is 100 story, so at every 100 floors, the lateral force which is generated at the ground level will be transferred at all 100 floors of your building will be there. And from that floor level, it has the aim of your building is to transfer this load which is coming on the floor level to ground again safely. So while transferring from the floor, from this diaphragm to the ground again, during this transfer, if this mechanism is disturbed, then there is the failure in the your beam or column, and due to that your structure gets failed. If this transferring of the load from the floor to the ground is done safely, definitely your structure is going to resist the earthquake and it will not get collapsed. So the mass of the building being designed controls the seismic design in addition to the building stiffness is there. So these two things are very important parameter, is the mass and the stiffness of the structure. So whenever we consider an earthquake, it is a dynamic force. That is a force which is which is a function of time is there. So in that case, whenever a force which is a function of time, definitely your all the responses in the structure like bending moment, shear force, displacement, drift, etc., will also be the function of the time is there. As in the case of the gravity force, the gravity forces are not a function of time. So in this case, they whatever the gravity load is there, same will be the response every time. They are not dependent on time. But in case when an earthquake comes, it is dependent on the time, and which creates has to be resisted by the mass of the building, and secondly by the stiffness is there. So the earthquake induces the inertia forces that are proportional to the mass is there. So whenever you write the equation of motion, so equation of motion is basically ma. So m a mass, that is the inertia force, then you write it for c is there, x dot is there, like I write m double x double dot, that is mass and acceleration. Velocity, if we say x dot, so x it will be in the proportional to the damping of the structure is there, and stiffness k multiplied by x will be equal to the input force in the form of an earthquake. So the inertia force, the damping force, and the stiffness force of the structure, which is on the left hand side, will resist the input force, which is on the right hand side. So this was also discussed that your earthquake motion comes in random any direction, but from simplicity point of view, we resolve it into the three components, and what your seismo meters are there, or the the seismological graphs generated at the recording stations are there. They are being given in the form of the accelerations in the longitudinal, in the vertical direction, and in the transverse direction. So there are two horizontal component and one is the vertical component. Generally, from the design point of view, that vertical component may be in the upward direction or maybe in the downward direction, and people generally neglect the vertical component of the earthquake, but there, in the past it has been seen that the vertical component can't be neglected. There are some evidences of the earthquake that as compared to the two horizontal component, the vertical component was more severe and which can't be neglected. As in the case of the IS code also, IS 1893-2016 says that vertical component, if you are not having, you can take it 2/3 of the horizontal or the lateral component in the earthquake. But in the case of critical structures like your water tanks or the pipelines are there, or dams or nuclear power plants are there, there the vertical component can't be neglected. So in the case of the horizontal components, you can see the horizontal components are in the inertia force and the lateral displacement, and no adequate, you have to need adequate load transfer path is there. This is the most important part which we will be discussing here, is a load path for the seismic forces is there, which already I have discussed with you, that the lateral force, that is the horizontal or the earthquake force, is in the horizontal direction. So first of all, it transfers to the horizontal members, that is it transfers to your horizontal diaphragm or the slabs. So this load path for the seismic forces is important. So the primary concern in the lateral or the horizontal force is that earthquake force is induced where the mass located, where the mass of a structure is located, the mass of the structure is located at the at the floor levels. It is located at the floor levels is there. So this force has to be transferred safely to the ground. So you need a load path. Load path has to be created. So this load path should have an adequate strength is there. So it has to be passed from floors to the walls or beams. If it is a load bearing structure is that, then it will the diaphragm load from the floors will pass to the walls and to the foundation. But if it is an earthen frame structure is that, so then it will be transferred to beams, from beams to columns, columns to foundation, and finally to the soil below. If this path is weak somewhere, then it forms what is the commonly known as the chain analogy is there, and this is what is the link. If any one of the link in this is weak one, then that may create a damage or the collapse of the structures. The weakest link you have to detect in the chain behavior is there. So if the building is subjected to ground motion, is idealized as a chain being pulled, then the link of the chain represent the building elements. So one like slab is there, one link is represents the beam is there, then columns, then foundations, and so on. So this path you can represent in the form of a chain, links of the chain is there. So as different elements have different characteristics, the link of the chain will also have different strength and deformability. So each chain will have, like each link will be different, because your slab will have a different strength, the stiffness will be different, and the deformation will be different. So accordingly, each chain will have a different properties in that case. So a designer can control the element strength by sizing and deformability by doing a proper detailing. So the strength of the chain is equal to the strength of its weakest link, and the ductility of a chain is governed by the ductility of its weakest chain. So your aim is to check that weakest link. अगर आपने वो कमजोर कड़ी पकड़ ली, then your structure is never going to fail in that case. So if we say a ductile link is there, if a ductile link is there, so if we draw a force deformation diagram for a ductile, it will be definitely, it will go elastic, then it will go plastic, and there will be a deformation, large deformation. But if it is a brittle link is there, then suddenly it will fail. Suddenly, like your glass is there or concrete materials are there. They are the brittle materials. So sudden failure or the collapse will be there. So, so you have to see this weakest one in this case. So if I say here, like 110 is there, 110 is larger than 105 is there. But if it is having a brittle link is there, then it will fail. It will fail at 105 is there. But if it is a ductile one, even if 105, it will carry 120 and so on. So increasing the element strength does not increase the performance there. Strength hierarchy rather than absolute strength is important in this case. So whenever you say weak link is ductile, strong link is your brittle one is that, then you are saying that it is a ductile behavior will be there. But if you make your strong link as a ductile one and weak as a brittle one, definitely weak. So how the failure will be there due to that weak link, and weak link is your brittle one. So how the failure will be that combined failure, it will be brittle one. So brittle link should be designed to exceed the capacity of the ductile link is there. So always your ductile link should be less as compared to the brittle link is there. Suppose your ductile link is 100, so obviously your brittle link should be greater than 100. So you want your structure to be behaving as a ductile link in that case is there. So who should fail first in a frame? Like we say in a RCC building is that the slab, it is making made up of the various components like slab, beam, column, foundation, and finally it has gone to the soil. So this is a hierarchy we see. If a slab fails, this is a load path we see. So in this case, if a slab fails or a diaphragm fails for a particular floor in a building, then it will affect that particular floor or that room is there. In that case, your building is not going to collapse. That particular room will have a damage, or that particular floor will have a damage. If a beam fails, it affects that story. If a column gets failed, it affects the building, and this is what we don't want. We don't want our columns to be failed here. So we go for the strong column, and the weak beams concept is there. If your foundation fails, then this is most serious part which was discussed by our previous experts, where they have shown you the soil structure interaction is there. So if foundation fails, it is very difficult and it is a more serious part. And even if your soil fails there, then it is even more serious, where if your soil is like black cotton soil is there, or there are some liquefaction damages in the soil is there. So in this case, you have to go hand to hand with the architect, with the structural engineer, and with the geological engineering. So the convenience is to providing the ductility is there. So the checks for earthquake resistant building is there. So you have to carry out some checks like being stronger than the adjoining frames is there. Your beam column joint should be stronger than the adjoining beams is there. Your column should be stronger than the adjoining beams there, and beam column joint stronger than the adjoining columns, and foundation should be stronger than the adjoining columns, and the soil strata underneath should be stronger than the foundation. If this path is done correctly, or if it is designed properly, the load path is done properly, then definitely your structure or your building will be earthquake resistant is there. So what are the four aspects are there which architects and the design engineers have to four aspects which the architects and design engineers have to work to create an earthquake resistant design. This was already discussed by the number of the experts. Like, I'm not going so much in details of these figures because it was shown to you. Like the structure, the seismic structural configuration, you have to see the size, shape, and the structural system carrying the loads are such that they ensure a direct and a smooth flow of inertia forces to the ground is there. So this was seen कि आपका your building should be having a symmetrical one, it shouldn't be an unsymmetrical one. Your plan should be in a symmetrical one, like square or circular one. You shouldn't go for like X cross sections or Y cross sections or C cross section shapes of the building is there. And it shouldn't be like the length of the building is very large as compared to the width, or the height of the building is very large as compared to the cross sectional dimensions of the building. So this is what the size and the shape and the structural systems are there, which affects the seismic structural configuration. The next important is the lateral stiffness is there. Its lateral load resistance system is such that the earthquake induced deformation in it do not damage its content under low to moderate shaking is there. So stiffness is in the terms of the dimensions of the, or the cross sectional dimensions of the structure, in the terms of the height of the building is there. So suppose the height of the building is H. So mostly you say the stiffness like 12 EI by L cube is there, or H cube here we can say. So ultimately your stiffness is proportional, inversely proportional to the cube of your height of the building is there, and it is also proportional to I comes the moment of inertia, where the cross sectional dimensions of the various structural systems come there, and E is what the modulus of elasticity, which relates the material of the structure is there. Next is the lateral strength is there. So the maximum lateral or the horizontal force that can resist is such that the damage induced in it does not result in the collapse. So ultimately your lateral strength is one of the parameters, and the ductility is there. Its capacity to undergo large deformation under the severe earthquake shaking even after yielding is, and it improved by the favorable design and detailing strategies is there. So this is what is being done by our code, like IS 13920 is there, which is for the ductile detailing. In all these four aspects, which are most important from architectural and the design engineers, are being covered by all the seismic codes is there. There are other factors which are to be considered, like the natural frequency of the structure or the time period of the structure. The damping factor of the building is there, what was discussed by the various experts, like if it is an RCC building, if it is steel building, the damping factor can't be neglected, because it is one of the important factor which causes the energy dissipation of your earthquake forces is there. The type of foundation is there, and the importance of the building is there. The importance of building is one of the important factor to be considered in the earthquake resistant design, that it should be operational after the earthquake also. So like your lifeline structures are like police stations are there, powerhouses are there, nuclear power plants, schools, as hospitals are there, your water tanks are there. These are the most important lifeline structure, and where they have discussed with you the importance factor of the building. Like if you are doing for the school building, the I factor has to be taken 1.5 and so on. For normal buildings, we take it as 1. So all these parameters are being considered in the earthquake codes. There are some few of the possible structural irregularities which increase the complexity of the structural behavior. The advice from earthquake resistant building, you have to make it simple. If you are creating more complexity in the structural behavior, you are disturbing the load path of the structure, and if this load path of the structure is disturbed, then you are disturbing that chain analogy, and finally the load will not be transferred safely to the ground, and there will be disturbance, and that will cause the collapse or the failure of the structure is there. So whenever an earthquake resistant design is there, it should be simple. It should not go for large number of structural irregularities. What IS code says that you can't neglect the irregularities, but there you have to give certain. They have given certain limits for the irregularities is there. So abrupt change in the geometry shouldn't be. You have to avoid these types. Is that these are some complexities there. Non-uniform disposition of the mass. Now, suppose all throughout, suppose you are having a 10-story building, and in all the floors the mass is same, no issue. But if at a particular floor you are increasing the mass, suppose at the sixth floor level you have increased the mass, so what has happened? It has created a non-uniform deposition of the mass. If you have made that particular floor as a storage, if you have created a swimming pool in that floor, is that without considering the increase in the mass is that, then it may disturb the structural behavior is that. So either you have to consider previously during the design of that structure, that calculations has to be done properly, then you have to design that structure is there. In between, if you are disturbing or you are creating a deposition of the mass, or you are increasing the mass in the floor level is that, then that may cause the uh, behavior of the structure will get disturbed in that case is there. That is interruption in the load path is there. Discontinuity in both strength and the stiffness. So the two important parameters considered in the seismic design of the RCC building is the strength and the stiffness is there. There are some chances, like in the RCC buildings, there are door and window openings are there. These door and window openings may create an stress path, indirect stress path around these openings is there. So there are some also abnormal proportioning of the structural members is that you have made a beam which is having a very large depth as compared to the width is there. You have not proportioned it properly. Or if the column you are making a rectangular one, the width of the column is very small as compared to the other dimension of the building. Your column is there, so you have to do proper proportioning of the structural members is that, so that the uniform load path is there and the distribution of load is done uniformly or properly. Lack of redundancy is that, which is the two most important part which I have discussed in my initial very first slide, is that there is the lack of redundancy and the lack of your ductile detailing is that. If these two things are done properly, then definitely your structure will resist the earthquake is there. So I will go for the stiffness distribution first of all. So we have seen in the previous slides like strength and stiffness is there. So the stiffness is that the horizontal stiffness of the building depends upon its height should be uniform. So in between, you can't say that a building, if you are making a 10-story building and your floor heights are like 3 meter each, but in between certain height you have changed from 3 meter to like 4 meter or 5 meter. It shouldn't happen. What is going to happen to the stiffness of the building? Suddenly at that particular floor where you have changed the height of the building, the stiffness of the building gets changed there, because your stiffness is what? It is 12 EI by L cube or H cube you can say. So it is inversely proportional to the height of the building is there. So your stiffness of that building. So probability is that probably you have to uh, plan a building which is having a height should be uniform in each floors is there. So what is going to happen? Your horizontal stiffness of the building will also be uniform. Change in the structural system of the building from one floor to the next will increase the potential for the damage and should be avoided. So this is what I have discussed you, that suddenly you can't change the height of the any floor, you suddenly can't change the mass of any floor is there. So these change in the structural system of the building from one floor to another should most probably be avoided. These are the very simple things which has to be considered in the design is there. But if you are not having any option, if your client or your customer is there and he says no, I want like this only, so you have to do proper designing of that particular floor as per the codal provisions is there. Columns or the shear walls should run uniformly from foundation to the roof is there without interruption or change in the material is there. So your columns, or it should not happen that there are floating columns in the building is there. Means the columns suddenly you have created, they are not going from foundation to the top of the building, but in between in some particular floor level you have created a column. Okay, it shouldn't happen. There is no foundation for the column is there. In between, at the diaphragm level or in between of any floor, you have created a column. So that is a floating column, and which is not running uniformly. So that may create a disturbance in the load transfer is there. And also the same condition is applicable for the shear walls also. Shear walls should also run from foundation to the complete height of the building. It should be there, and there should not be some interruptions or change in the material is there. That in the shear wall, suppose you have made a shear wall in a particular region as a RCC, then you are say taking it as a precast one. No, it shouldn't happen. It should be a uniform one in the material also. Next, increasing the column size increases both stiffness and the mass of the building is there. So this concept, what is there is, we will be discussing further also in coming slides, is that strong column concept is there. So how you can make the column stronger as compared to widths? The only option is to increase the size of the column. So ultimately you are increasing the stiffness and the mass of the building is there. But when the percent increase in the stiffness as a result of the increase in the column size is larger than the percent increase in the mass, the natural period gets reduced. So this is what is that your time or the omega or the frequency of the structure is equal to root of k by m is there. So your frequency is proportional to the stiffness of the structure, while your frequency is inversely proportional to the mass of the structure is there. So these basic parameter you have to consider. Otherwise, the time period of the your structure will get disturbed. So you have to do proper proportioning of your the stiffness and the mass of the structure is there. So the time period, if you say a time period in a particular region, so this is what is given in your IS code is there as per the zones is given. So this precaution has to be taken by the code in the form of the zones, zone 2, 3, 4, and 5 is given to you. So accordingly, and all your like SA by G parameter, what you are determining while calculating the horizontal acceleration, when it was discussed by the previous experts also, like when you are calculating the base shear of a building is there, it is the equation related to SA by G, and their SA by G, the graph was shown to you. This SA by G is the value which is being given with respect to, all of you might be knowing, it was discussed by number of the experts in our case, is that this value, this is SA by G which is given. And the horizontal, this most important part is this horizontal, and this SA by G value is dependent on the time period of your structure is there. This is the frequency of the structure is there. Now, if the frequency of your structure matches with the frequency of your earthquake is there, then definitely there is a resonance is there and your structure is going to get collapse is there. So this time period of the structure is most important part in designing an earthquake, and this time period depends on the stiffness and the mass of the structure is there. So building are said to be have shorter natural period with increase in the column size. So if you are increasing the column size, what is going to happen? You are increasing the mass, and what is going to, so your time period or the omega or the frequency, the frequency, that is your k by m is there. So if you are increasing the mass, what is going to happen to the frequency? In this case, it will get here shorter is there. Your natural time period T gets here shorter. Next, here we have discussed related to stiffness distribution. Next, two important parameters which I am discussing is the stiffness and the strength is there. The second one, the strength is there. So strength, the lateral strength of RCC building depends on many factors, like which was discussed also previously, like structural sizes, the configuration adopted, the material strength and the ductility, the relative sizes of the structural members, amounts of reinforcement used in the members, and strength and the stiffness of the joints between the member is there. So here we can see the two plots are there where the building having different strengths but same ductility is there. So what is going to happen in this case is there. So here you can see the strength is there. So there here the deformation, the strength carrying capacity of different strengths they are same, but the ductility here you can say is the deformation is same here, and here it is different. The ductility is different. So you can see one building is having the deformation different, the another one is having different, and the it is having the different deformation is there. So the different ductility, so your aim in this case different strengths are there here and the same ductility, and here there is the different ductility is there. So one of the is that the collapse mechanism. This is the most important part in the frames of the building is that collapse mechanism. So as a structural designer, you must have in your hand that how your building is going to fail. That is, it must be in your hand that you want how which type of failure you want in your building. So accordingly you design your building. So if we want a ductile failure or if we want a brittle failure is there. So how you can do it? Undesirable failure with plastic hinges only in one story. So this is what is the undesirable failure. You have designed in such a way that plastic hinges are formed only in the one story is there. Even if it is having a small displacement at the collapse state is there, but this is an undesirable failure is there. What is going to happen? This is a behavior of a soft story is that in that case your plastic hinges are concentrated only in the particular soft story, in a particular one story only. But if you are making this type of a desirable failure in which the plastic hinges are formed in all beams is there. So what you want, you are making beam. Beam is weaker as compared to the column, what we have seen in the previous slides also. Like the damage, where the damage will be there, the damage will be in the beam part. So damage damage distributed in all stories will be there. There will be large displacement at the collapse state is that. But what is the desirable? That plastic hinges are formed in all these beams. But the column has not collapsed. So if your column is not having any collapse, definitely your building is not going to collapse. It will remain stand. So the strength and the stiffness irregularities should be eliminated. And by choosing a proper structural system does not make the irregularity. So you have, what we have discussed here, that your structural strength of RCC building depends on the proper structural configuration and the material what we are adopting. So for instance, by running a suitable RCC structural wall that run through the full height of the building, this irregularity can be made marginable. So there are collapse mechanisms. This might, all of you might be knowing, you might have been teaching to your students also, that one mechanism is the sway mechanism in the building is there, and the another one is the sway mechanism which is in the story is there. So if we compare these two mechanisms is there in the form of the force deformation diagram is there, definitely if we plot the force deformation diagram for a building sway mechanism is there, so we are getting this type of an curve is there, and this area of this curve is less. So what is going to happen? Area enclosed represents the energy dissipated or absorbed is there. While in the case of story sway mechanism, you can see the force deformation diagram, the area enclosed is larger one. So what is going to happen? The energy dissipated, or based on the material what you are using, energy dissipated or absorbed will be larger one because the area enclosed is more. So what is going to happen if we compare between a building sway mechanism and the story sway mechanism is that in building sway mechanism, the damage are concentrated in the columns, that too in a single story, what we have seen. So this type of a mechanism, this type of an undesirable failure, which we have seen is the building sway mechanism. While the desirable failure, this one is that what we have seen in the story sway mechanism is there. So ductile demand of the column is larger in this case because all your damages are or the plastic hinges are concentrated in that particular one story and in that columns is there. So the ductile demand at that particular column will be larger, and this type of building has weak column and weak column and strong beam design is there. Okay, but if I go for the story sway mechanism is there, which ensures that beams yield before the columns is there. We want this type of failure only. What we have seen in the load path pattern, which we have discussed in the chain analogy also, that beam yielding should be there before the column is there. And how this mechanism will be there? It will be the ductile flexural damage occurs at the beam ends will be there. The buildings in this case will be having a strong column and the weak beam will be there. So what is going to happen in these types of the large area is enclosed in this for the deformation curve is there. So good energy dissipation in these types of building will be there through each of the inelastic hinges at the beam ends will be there. So the good energy dissipation, what we want, the energy should be dissipated. So earthquake is nothing but it produces an energy. So that energy has to be released from your structure. Either your material should absorb it or it should dissipate it. So what we have seen using the various vibration control systems which were discussed by our experts is that the passive control systems and the semi-active, active and the hybrid control systems are there. All these are what they are doing. They are either absorbing or dissipating this earthquake energy is there. And the other one, the building sway mechanism, less energy dissipation in these types of building is there, and that too all that energy is concentrated in one story only. So this is the figure which shows the strong column and weak beam is there, and the another one is the weak column and the strong beam is there. So definitely if you want to stand properly, you want to run, or if you want to walk properly, your legs should be stronger as compared to your hands and other parts. So आपको खड़ा होना है. So who are the legs of the building? The columns are the legs. So you can see here this is an figure of the base shear of a building and the roof displacement. The plots is given for the for these two buildings is there. Here you can see the deformation of the roof displacement for the strong column beam is more as compared to this weak columns is there. So the failure, this was already discussed by the professors in the previous expert talks also. So I'm just going through it. Then failure of column can affect the stability of the whole building, but a failure of a beam causes a localized effect, which was discussed here in the previous slides also. So it is better to make beams to be a ductile weak link than the columns is there. So in the designing of a RCC building, strong column weak beam design method should be adopted. I am skipping this part. This was already discussed that the summation of moments of the column should be greater than 1.4 times the summation of the moments coming from the beam is there. So what you do to make the beams as a ductile weak links in the case of the shear reinforcement should be adequate to ensure that the shear strength exceeds the strength of the flexure is there. So you want your beam to be having a flexural failure and you don't want your beams to be shear failure. So your flexural strength should be less as compared to the shear strength is there. So how you can increase the shear strength capacity of a beam? By increasing the shear reinforcement, that is the stirrups. Okay, so you can decrease the spacing between the stirrups is there. So thus prevent a non-ductile shear failure is there. So this is the failure where mostly it is a very well defined failure in the case of RCC buildings is there, and which I think so these types of pictures were shown previously also, but I am discussing it related to the weak column. So here you can see that the your column has collapsed, your slab is there, the beams are perfectly there, they have not collapsed. So this is the concept where the weak columns are there and strong beam is there. This is one type of a damage which is also known as the pancake damage is there. This is also an example where in a Bhuj earthquake in 2001 where the you can see one above the floors are resting. The column has failed and the floors are resting one above the another like a pancake is there. This is also a damage due to the weak column concept is that you can see the building beams are standing, your slab is safe, but your columns have failed. Now, this is one of the important which I was discussing previously also, that your walls or in the form of a shear wall, etc., has to be provided throughout the height of the building. It should go from the bottom of the building to the top of the building. It shouldn't happen that beach may apne you have constructed a column, you have constructed a wall in between is there. It shouldn't happen. So by using a walls of full height provide a reasonable uniform stiffness and strength along the height of the building. This is the most important part is that when you are basically writing an equation of a motion for a structure is that, so there is one parameter which has to be considered, and that is known as the structural plant density is there. So the ratio of the area of the vertical element resting the lateral load to the plinth area of the building is called the structural plant density of a building is there. And generally your SDP is low for the gravity, only the design of the buildings around 2% or less, and increases for the gravity plus lateral loads, and it has to be taken like 4% or more is that. So whenever you are considering the earthquake forces or the lateral forces plus gravity forces in your load combinations is that, then your SDP should be 4 or more than 4 is there. So what SDP can taken as a measure to reflect the overall performance of your building. So you have to take care of this parameter also, like the structural plant density. So what is structural plant? It is the area of the vertical elements resisting the lateral force to the total plinth area of your building is there. So this is an example where the SDP is being plotted for different SDP values varying from 0 to 6 is there, and the performance of that moment in the interior columns is being shown. So here you can see the performance of the SDP for the SDP by use of the walls is definitely more beneficial, and it will increase the earthquake capacity of your building is there. Next one is the structural unsymmetry in the plan is there, which was discussed by the previous class also. Like they have discussed the effect of soil structure interaction in the asymmetrical building like T or C-shaped buildings is there. So what is going to happen in the unsymmetrical plan of a building? This is definitely going to create a twisting or the torsional effect in the building, and which will affect the structural behavior during and lateral or the earthquake forces is there. So what is going to happen in that case? So if you are making the asymmetrical in the plan is there, so what you are going to make that the center of the mass and the center of the stiffness do not coincide in the planning any floor level, and the building get twisted or there is the torsion in the building, and this will create an additional lateral forces, additional bending moment in your building will be created. And so the weaker columns reaches their strength limits, stiffness deteriorations in these columns will result, and this results an asymmetry, and due to which your what is going to happen, the twisting or the additional forces will be created. And if there is an unsymmetry is there, what is going to happen? Your cross sectional dimensions, your reinforcement required will be more, so your structure will be what, it will be expensive, it will be costlier one. So better is to make it simpler one, to make it a symmetrical plan building with a uniformly distributed mass and the stiffnesses. This is the what already I have explained you, that is the strength discontinuity in the elevation is that there shouldn't be sudden reduction in the lateral strength of the building is there in the form of your open or flexible or weak story, in the form of your soft story is there, where you are providing an openings, there is no infill in the ground story is there, or suddenly what you have done here, the columns are stronger one, and then you have made the columns dimensions less. Here the column dimensions are made. Sudden change in the member sizes are there. So there is abrupt change in the column sizes has happened. So here the concentration of your forces will be more in this. This becomes a weak part of your. This is the weak chain in your chain analogy is there. So there is a generally people say soft story where the brick your infill machineries are not provided. It is commonly at the ground stories are there, so that story is also known as open story or flexible story or weak story or soft story. The people refer the different terminologies there. So here you can see the buildings which is a bare frame building without any infill, how it behaves, the force deformation diagram, that is the base shear and the roof displacement plots are shown here. Here there is an open story at the ground floor is there, here the open story at some in between roof floor is there, and total infill machinery is there. Definitely what we have seen in the previous lectures also, that infill machinery behaves um, more resistant to earthquake forces as compared to these types of the weak story building. These are some collapse of the buildings where the soft story collapse mechanism was there. I am going a little bit fast because already it was shown to you. Soft story. So here the particular story, you can see this third story was acting as a soft story. So whole building is proper. That soft story has get collapsed there. This is what I'm telling you, that the discontinuity of the structural wall in building should be avoided. It should be continuous one. To avoid this type of irregularity is that, so it shouldn't happen. You shouldn't do like this. This shouldn't happen. This shouldn't be there. The best option is to provide it from foundation to the total height is there. So ultimately, you are not disturbing the stiffness and the strength of the building is there. One more concept which is mostly considered in the building is the short column effect is there. This short column effect, the short columns are there which attracts the large horizontal forces as compared to the tall columns are there. You know the slenderness ratio. So based on this slenderness ratio, we decide whether it is a short column or a slender column is there. So the short columns are stiffer, and due to that they attract more earthquake large forces as compared to the slender columns is there. So the stiffness of the column means the resistance to deformation. The large is the stiffness, the larger is the force required for its deformation. So if a short column is not adequately designed for such large forces, it can suffer significant damage during an earthquake, and this behavior is known as the short column effect. So there is one additional clause given in the design. If you have gone for the IS 456, there is a design for the pedestal is there, and that takes care of this short column effect is there. So I am little bit skipping this. I will just explain you with the help of these figures. So these are the some examples where the short column effect is there in the buildings. Right, if the buildings are provided on the sloping ground is there, so one of the column is a short column, and one of the columns on one corner is a tall column. So here the short column effect is there. Or if in columns you have provided in between a mezzanine flooring is there, so this creates a short column effect in the columns is there. You have changed the boundary condition, the height of the column is being changed. You can see if the machinery is not provided throughout the height of the building, if you have provided machinery at only for a particular height of the floor is that, then this column will be acting as a short column. This column will be acting as a short column because you have provided the partial height of the machinery wall is there. These are the regular columns, okay, but these columns will be acting as a short column is there. Short column effect owing to the masonry infill adjoining the RCC columns is there. So these becomes a short column connection. So these are the chances where these columns will get damaged during a lateral forces there. You can see a lateral force is acting, lateral force. So these columns will be subjected to the damages there. So the effective height of the column over which it can bend is restricted by the adjacent walls is there. And this short column effect is more severe when the opening heights are provided smaller as compared to the height of the column is there. Now this is what we study in the case of the boundary conditions of the column is that, like, you go for the slenderness ratio of the column is there. So this height gets changed if you are providing the partial height of the masonry infills are there. Short column effect is also seen in some of the RCC columns. If you are provided, it means the mezzanine flooring or the loft slab is provided. This type of bracing systems in between, or K bracing systems, or staircase beam is provided, or this type in the case of the plinth beams in the ground story where the columns are here. These are the short column effects are there. Even when the it is on the sloping ground, which already I have shown you. So these are the some examples, and you have to take proper precautions in the design of these short column effect in the buildings is there. These types of floating column effect, short column effect here, this is a floating column effect. These are where the alignment or the column, you have changed the position of the column. They are not properly aligned in one line. So what has happened here? The load path will not be proper. It should go aligned in the vertical direction in the column is there. But in between, you have disturbed. Here you have disturbed the alignment of the beams. Here you have disturbed the alignment of the columns is there. Here you have changed the, suddenly the height of the story is there. So this creates some short column effect, and the load path you have created. Here also, this is a very typical example where suddenly a column was from the ground story up to one story, and it is being break, and again it is started. So this type of precautions you have to take to avoid this thing, and this is what creates a weak link in the building is there. So these are the some short column effects in the building in the form of a staircase. You can see where the staircase is providing this staircase landing part is there, the short column effect. These are the failures of the short column effects in the building, and mostly the short column fails due to the bulging action is there. So the bulging action is there, as you, if you compare the failure pattern of a tall column and a short column is there, the short column fails due to bulging, and your tall column is having a bending effect, bending is there. So if a short column is there, this type of failure is seen. The X type of an failure is commonly observed in the case of the short columns is there, and which is due to the shear failure is there. This is also a typical example of a short column effect in the building is there. So short column is a brittle failure. You can see a reinforcement is as it is, but your concrete has been get failed here because it is a failure due to the shear failure is there. Here also you can see, here you can see how the reinforcement has bulged out because it is having a bulging effect is there, bulging short column effect is there. Now IS 1893 2016 recommends that building to be these are the lateral stiffness strength criteria given in the IS code. In the IS code clause, if you go through IS code, they have given the lateral stiffness in any story should not be less than 70% of that in a story above, or less than 80% of the average lateral stiffness of the 3 stories above it. So whenever you are changing the stiffness, the above and the below story, it should not be less than 70% is there. If you do a combine between the 3 stories, should not be less than 80% of the average lateral stiffness is there. Similarly, in the case of the lateral strength also, IS code says that in the case of strength, we generally say it in the terms of the mass. In any story, should not be less than 80% of that of the story above is there. So these precautions has to be taken while designing. You have to go through the codal provisions properly and then design the building system. So the distribution of the lateral strength and the stiffness along the building height needs to be determined to identify an irregularity in the lateral strength and the stiffness is there. IS code has given you the various irregularities in the form of the mass irregularity. This is the stiffness irregularity is there. There is torsional irregularity. There are setback irregularities also given in the IS code 1893 is there. And then lastly, the ductility is there. So in my presentation, I have discussed the seismic behavior of RCC building with respect to the four aspects which has to be considered in the design is that. So one of the factor is the ductility is there. So in short, I am just discussing related to the ductility is that you have to increase the ductility. So how you can increase? You can make a simple and a regular structural configuration, which is the basic aim of the earthquake resistant design of a building is there. Using more redundancy of the lateral load resistance system is that, and you have to avoid column failure by adopting the weak beam and the strong column principle in the design is that you have to avoid the foundation failures, you have to avoid the brittle failures due to the shear, bond, anchorage or the compression failure in the bending is there, and you have to provide what you can do now. You have to do the proper lapping of the vertical reinforcement, you have to do proper spatial confinement of the concrete at the critical points, at the beam column joints is there, at the column foundation joint is there. You have to do proper confined reinforcement as per IS 13920 is there. So by the provision of lateral these, so that the concrete can undergo large compressive strain before the failure is there. And the lastly, most important part in the case of beams, as we were studying in your our bachelor's also, that your beam should be designed as an under reinforced section so that it can undergo large rotation before the failure. So you want your structure to fail as a flexural one. So you have to design accordingly your structures. Now next I will just discuss the some work done by our students where there is a strengthening scheme for the soft story building where we have studied there. So there was an RCC frame building was considered. This is an RCC frame building. You can see it was G+10 building is there. And then we have studied it for the masonry infill with soft story. So here the masonry infill was provided for all the stories, and there was a soft story. These are the reinforcement detailing and the column cross sections for the beam and the columns, and the reinforcement detailing is there. These are the these are the masonry infill RCC frames with soft story is there. These are provided here. So हाँ सर, हमारा सेशन चल रहा था इसमें. हाँ सर, 4:40 तक बोल दीजिए सर. हाँ, हम बस छोड़ ही रहे हैं. हाँ, छोड़ ही रहे हैं. 4:20 हो गया, हम छोड़ ही रहे 10-15 मिनट में. हमारा सेशन चल रहा है. ठीक है, ठीक है, हम खत्म ही करते रहे. ठीक है. हाँ, ठीक. Am I audible?
Yes, ma'am. Audible.
Okay. So here the masonry infill of an RCC frame with soft story was there. Then what is being done? We have provided in a soft story 33% infill. Then further we have taken 66% infill, and then we have strengthened that soft story with the shear wall is there. So this is the paper which is published. You can refer this paper also. It is available. And the comparison is done, and further we have done strengthening of this soft story. So one we have done with partial infill, second we have done with the shear wall, and then we have done the strengthening with FRP. Here FRP we have used the glass fiber reinforced polymer GFRP and carbon fiber polymer of 1 mm thickness of the modulus of elasticity 70,000, and it was taken as 2 lakh this 2,15,000 megapascals the E value was taken, and you can see how the soft story columns are being wrapped with the help of these FRP is there. So this is what the strengthening technique was there. And one more strengthening technique which we have done is to provide the eccentric bracing. So because as it is a parking, so we have to allow for the parking of the cars, etc. So the eccentric bracing were used for the strengthening of the soft story was there. This is the dimensions of the eccentric bracings are shown here. So eccentric bracing was used with the various steel sections like the hollow rectangular section, hollow circular section, equal angle section, T section, channel section, and the symmetrical I section. So we have studied it for all these 6 sections for different sections which were used for these eccentric bracings. So then the pushover analysis was carried out as it was discussed in the our today's first session, where the performance was studied, and this study was carried out in Sysmosoft software which is freely available. So the pushover analysis for the frame strengthened with infill, so the infill of 33%, 63%, and soft story was compared with the complete infill frame was there. So obviously the complete infill frame building will perform better as compared to 33% infill, 63, and you can see the soft story frame will perform less is there. Next, then the pushover analysis or the performance curves were studied for the soft story, and with the 2 FRPs which we have considered for the strengthening of the soft story columns was then further the eccentric bracings which were used with the hollow square sections, and here you can see the cross sections of these hollow cross sections were also varied. Like we have taken cross section 25, 50, 100, 200, 270. So you can obviously see as the cross sectional of the square hollow section increases, definitely the performance will get improved. So here you can see here the performance is better as you go on increasing the cross sectional dimensions. Here the performance of the hollow circular section is also shown. Here also we have varied the diameter of the hollow circular sections. Similarly, for the angle sections also, for the varying angle sections like 70 cross 70, 80 cross 80, 90 and 100 are compared here, and the performance were studied, and for the T sections also. And finally, for the channel sections and for the I sections, the performance were studied for the pushover analysis is there. So the finally, what is the performance point what we are getting? So a comparative table between the partially infilled shear wall, FRP confined column is there, then you are using the eccentric bracing systems with the different sections, the roof displacement and the base shear performance of these various frames were studied, and the performance points were determined that which is better for the strengthening scheme of the soft story building is there. So finally what was done here, that this is for the roof displacement what was shown, but if you do it for the first story, because your first story was a soft story where the concentration of the displacement was larger as compared to the other stories, if you compare this performance of the reduction in the first story displacement in the strengthened frame is there, here you can see that the shear wall performs better because the reduction here is 98.76% as compared to the soft story building is there. As compared to the other, the eccentric building also performs better, and this is what is being done for the first story displacement. It is compared. So the first story displacement is the critical in soft story buildings, and the strengthening schemes are compared based on their capacity to reduce the first story displacement, and it has been observed that the shear walls perform better, even your eccentric bracings also perform better, and there is a reduction of about 75 to 85% in the story displacement is there. So next study we will continue with the one more study which was based on the irregularities, and which was the vertical setback irregularity, and vertical setback irregularity is in the form of the elevation is there. So these are some typical examples of the structures where there are vertical setback irregularities. So these are the various models you can see. This is the RCC building, which is having an regular model is that. Then we have provided a setback. Setback means in between only some stories you have removed. There is a setback irregularity at second story is that, at fifth story is that, at the eighth story is that, and even the setback irregularity was provided in the form of the two steps also. Like this is the one step irregularity of setback is that they are provided a two step irregularity also, and you have provided these types of. So these are the typical examples, and these has to be avoided. Here we have carried out the time history analysis. So previous example which I have discussed was based on the performance one. This is based on the time history analysis where an incremental dynamic analysis was carried out. So here we have actual real-time earthquake like Kobe 1995 earthquake, Loma Prieta 1989 earthquake, and Northridge 1994 earthquake, where as an input were provided to these different frames of the setback irregularities, and we have studied the performance in this. This was G+10 residential building of floor of the story height 3 meter. These are the various descriptions of beam and column and the various properties of the this RCC building. So these are the time histories. You can see time versus acceleration, time history for the 3 earthquakes which we have considered. This is the time period of the models we have considered. These are the time histories for the Loma Prieta earthquake. You can plot the time history each floor level for the different parameters like responses, how you are measuring acceleration, displacement, base shear, bending moment, and so on. We are plotted, and the vertical graphs were plotted for the different story height and the absolute acceleration. On the x-axis, the parameters were changed like absolute acceleration, displacement, base shear, bending moment, axial forces were carried out, and along the height of the building for different models, the responses were plotted. These are the peak responses plotted for a particular time. If you see here, the peak response what we are getting, irrespective of the time, we are being plotted here. And finally, what we are getting, like this is the displacement curve is there. This is the story drift curve is there for the Loma Prieta earthquake. For all 3 earthquakes, the different responses plots were carried out. And finally, what we can say here is that as the vertical setback irregularity in building increases, the fundamental time period of the building decreases, which we can see from this plot also, that for a regular building, the time period was 5.54 seconds, and as the irregularity was there, it can be seen as 3.8 seconds was there. So the setback irregularity in building model introduces the displacement, story drift, shear force, bending moment increments along the height of the building is there. It can also be observed that the story displacement, story drift, shear force, bending moment with vertical setback irregularity at mid height of the building is more as compared to the irregularities provided above and below the mid height of the building. So mostly you have to avoid the irregularities at the middle height. So either irregularity at the bottom side you can go, or at the top side you can go. But mostly you have to avoid in between the mid height of the building. These are having more responses as compared to the if irregularity is provided above the mid height and the below the mid height of the building is there. So it can also be seen that multiple setback irregularities develops more story displacement as compared to the single step irregularity. So multiple setback irregularities which is shown here. This is a multiple setback irregularity. This is one of the example of multiple setback irregularities should be avoided in the buildings. So proper analysis of these types of irregularities in the building has to be carried out. So finally, what we have studied in the last 5 days is that I think so, based on the Henry, an earthquake engineer of US, is that if we have a proper configuration to start with, all the engineers can do is to provide a band-aid or improve a basically poor solution as best as we can. But if we start with a good configuration and reasonable framing system, even a poor engineer can't set ultimate performance too much.